Yeah, so it's a great pleasure to have Wouter and Limbeek from UIC, and he'll be telling us about commensurators and arithmeticity of hyperbolic manifolds. All yours, Wouter. Yeah.
Thanks, man.
Thanks for agreeing to give this talk. Yeah. Great.
Well, thanks for coming at, I believe it's 8 p.m. for you. So
yeah.
Thanks for showing up so late in the evening. And thanks for the invitation. It's I'd rather be in India physically, since it's -5 here, and I think it's warmer over there. But I'll take this. So I'll be speaking about this project, which is joined with David Fisher, who I believe is speaking next week in this seminar, hopefully about something else, or so hopefully about a different result. And Mahan. Okay, so let me start by motivating it by the following by the following geometric problem. So suppose that M is a finite volume hyperbolic manifold. And what I would like to do is to study the symmetries of M. That is to say, just a group of isometries. Okay, and by study, I mean, whatever you would like to know, but for example, something that appeals to me is to try to classify M with the most symmetries, whatever that means. I'll make it more precise in just a second. But before doing so, I would like to first rephrase this as an algebraic problem instead. So I think everybody knows. So let's say I have my M, I have some isometry. I can lift this to the universal cover. By the way, if there are any questions at any point, please interrupt, either by audio or in the chat. I'll try to keep track of the chat, but no promises.
So Wouter, I'll take care of the chat. Yeah.
Okay, thanks. Yeah. So I lift F to the universal cover, and I get some isometry over there. So if F is in some M, then this lift is in isometry group of the universal cover. And just to make things a bit easier to write, I will write G for isometries of hyperbolic space. All right, and okay, that's good. And if we write M as hyperbolic space modulo some lattice, then we can realize, so this isometry group of M is a certain, so it consists of certain elements of G, which are these lifts. And which lifts do you get? Well, you just get the normalizer of gamma in G, where gamma is this fundamental group, modulo gamma itself, right? A deck transformation up here will descend to identity down there. And now there's some bad news for my question over here, which is, and maybe everybody knows this already, but the bad news is that this group is finite. So this normalizer modulo gamma is always finite. Okay, and so the rest of one possible future for this talk is that I now turn into a finite group theorist, and I try to study this this problem of how large this can be, but that is not the direction I want to take. And I would instead like to change this geometric problem here, and instead of studying symmetries, I would like to study virtual symmetries. by which I mean not isometries of M itself. Actually, I'll leave this up, but just cross it out. Instead, I would like to study isometries between finite covers of M. and then I would like to classify M with the most virtual symmetries. And what algebraic problem does this correspond to? Well, if I have, instead of having an isometry of M, I now have an isometry between two finite covers. Okay. And I can also lift this to hyperbolic space. But of course, I do not get the element that I get here. It doesn't normalize gamma because it's not a map from M to itself. It's only between finite covers. And so what it turns out is that, let me put this here, is that a virtual isometry let's say the picture is like this. Corresponds exactly to an element of G if you lift it, such that, well, what you do is you conjugate gamma, and instead of being equal to gamma, that was what was before, it just slightly moves gamma off of itself. So if you look at this intersection, it lives in each of these two subgroups. And what I demand is that each of them is a finite index inclusion. Okay. And such an element I call a commensuration. Of gamma. Now, key definition for the rest of the talk is that the commensurator of gamma is the subgroup that you get by it's just all commensurations. Okay, and so this subgroup of G, it sits inside G, somehow classifies all the isometries between finite covers of M. And now, kind of a cool observation is that even though the group of isometries of M is always finite, this is not true for these virtual isometries. So there can be infinitely many virtual isometries that are, let's say inequivalent. Sorry, let me move this over. Inequivalent. Where I say two virtual isometries are the same if on a further finite cover they coincide. Or if you like, it can happen that gamma is infinite index in its commensurator. This should not be obvious, but it's just, for now, it's just a remark, and I will show you in a moment how this can happen. But before that, so let me, instead of writing the commensurator, I will just introduce the following notation that delta will always denote the commensurator of gamma for this talk. So my new problem then that I want to discuss today is to classify M, or what is the same, classify gamma with a large commensurator. Okay, so as I promised, I would be a bit more specific what large means. And there are at least two things you can say. You could either hope to classify gamma in delta where it's just infinite index. So, which is to say that you get infinitely many virtual isometries. But actually, this turns out to be the same as, let's put it like this. This is the same as delta is dense. And if you already know all of this stuff, or if you get bored with the talk, then you can prove this equivalence. But so this will be my goal, to classify M where either this condition or this condition holds. And that's as large as you can hope for the commensurator to be, that it's dense in G. Any questions so far? All right, so fortunately, this has been done. So not our result. One direction is due to Borel about 50 years ago, and the other direction is due to Margulis. And they proved that if you have dense commensurator, then this is the same as that gamma is arithmetic. Okay, and Borel did, let's see. So when I state it like this, Borel did this implication, and Margulis the other one. Now, question. So I'm not sure in this seminar, do I need to, I probably need to say a bit more.
Yeah, it'll be a good idea if you say what arithmetic is.
Yes. Okay, good. So what does it mean, arithmetic? Maybe before doing that, let me just give them the full credit that is due and say that actually they proved this not just for G isometries of hyperbolic space, but for any, maybe I'll say it like this, for any semi-simple group. G, Lie group, and any irreducible lattice. Gamma in G. So what is arithmetic? The complete definition is a bit technical. So let me avoid that and just give you an example. So if G is SLNR, then I could take gamma to be SLNZ, and that would be an arithmetic lattice. And in general, it looks like this, except instead of Z, you basically it's rings of integers of number fields. So more generally. Yeah, so maybe I should just say gamma. You can always realize gamma as the integer points of some algebraic group. And even that is a bit of a lie, but if you know why that is a lie, then I think you also know how to fix it. So, but really this is the idea, that you just look at integer matrices. And so the group theory of this lattice will be connected to the number theory of this algebraic group. Okay, I should say that for many Lie groups G, so if G has rank at least 2, whatever that is, but then any lattice is arithmetic. This is another closely related theorem of Margulis, closely related to the one that I just stated. But if G has rank 1, this is not always true. And in particular, we will just be interested in G is isometries of hyperbolic space. So that's a rank 1 group. So in particular. There are non-arithmetic lattices. Okay, so this theorem, let me just back up a second after this digression into arithmeticity. It's a really amazing theorem because, well, at least for me, I view this as a geometric condition. It says in this manifold, well, the manifold itself cannot have that many symmetries because the isometry group is finite. Between finite covers, there are lots and lots and lots of isometries. And somehow this can only occur if gamma comes from this number theoretic construction. So on this side, it's algebra, and on this side, it's geometry. And maybe I should say also for this specific example of an arithmetic lattice, what would delta be? In this case, delta is just, actually, this is kind of a lie. Let me, okay. So if you're very astute, then you see that this is a lie, and to make it actually true, I should put PSL everywhere. But let me ignore this. It's a very technical point. So please ignore that if you if you want. Okay, so good. So the question has been answered. But now after that, for a while, nothing. But eventually there was the following question. This is due to Shalom, which I'm not actually sure the history of this question, but the first time it appeared in print was in 2011, although I think it's been around before. And Shalom asked, what if gamma is not a lattice? Or more precisely, is it true that if you just have, and let me just state it for G is isometries of Hn because it's slightly simpler. Is it true that if gamma is any infinite discrete group, and delta is dense, then gamma is arithmetic. That's Shalom's question. And maybe I'll just say that for those people who care about other Lie groups, it's the same question, but you should ask, instead of gamma just being infinite, you should insist that gamma is Zariski dense. Okay. Well, why do you care? I think maybe it's hard to care about this question at the moment because, okay, maybe it's nice to think of virtual isometries of Hn mod gamma when gamma is not a finite volume hyperbolic manifold, but these spaces can get quite crazy. So it's not clear that there is any, that this kind of nice answer should be possible. But let me describe for you a connection that I find very appealing. So suppose that suppose you were in the following situation. Suppose you had delta inside a product SLNR cross, or really it could be isometries of Hn, I don't care. But the second factor, I make it p-adic. If you're not familiar with p-adic groups, then it's okay. Just I think you won't lose much if you just pretend it's SLNR. Although for technical reasons it won't work here, but it, you know, informally it should. So suppose that you had this, and suppose that this is a discrete subgroup in this product and irreducible. So what should irreducible mean? By irreducible, I mean that delta does not lie in a smaller product. Delta is not contained in any, whoa, that's, delta is not contained in any smaller product. Or equivalently, this irreducibility is the same as delta has dense projection to both of these factors. Right, so delta lies in this product. You can project it to either the first factor or the second factor. And then you ask that it's dense in both of them, even though in the product it is discrete. And this kind of thing happens all the time. For example, a good group that does this is when you take SLN integer entries, but now not just integer entries, but also everything with denominators involving some prime p, where this p is the same prime as this p. It turns out that this group has this property. Okay, then what you can do is set gamma to be delta, or maybe maybe I should write it like this. All those elements of delta such that the projection to the second factor so which lies in this SLN QP actually lies in the integer points. Belongs to SLN ZP. Okay, so that's some subgroup. And then you can check exercise again, if you are bored with the lecture. You can check that gamma is discrete in SLNR and delta commensurates gamma. And for this second property is essentially because SLN-QP commensurates SLN-ZP. Okay, so why is this useful? Just zooming out a little bit. Why is this useful for my problem? So if you think about this question, then one way to make such a gamma and such a delta is to start with this construction here and then take gamma as over here. And so Shalom's a positive answer to Shalom's question implies that you know, any delta, as in the example, is actually an irreducible lattice. Because yeah, I'm skipping a few steps that I will actually say a little bit more later, but Shalom's question would imply that this gamma is a lattice in the first factor, and if gamma is a lattice in this part, you can prove that delta has to be a lattice in this product, which I think is quite strange that the only irreducible subgroups in this product would be lattices. I don't know if you believe that or not, but so it goes both ways. If you can build a counterexample to that, you have a counterexample to this question of Shalom. And maybe related question is, are there irreducible subgroups in, let's say, H2 cross H2, or acting on? So they would be in isometries of H2 cross. So I think if you, for the people who work in this business, you see irreducible lattices in here all the time. But it could be that any irreducible subgroup is actually a lattice. All right, so that's just one reason that one might care about this question of Shalom. So now what do we know about it? Maybe I should, sorry, let me copy the question. Here was. Okay, so here's what's known. The first result, which is way before Shalom asked this question, is due to Greenberg in '74, and is that this is true whenever G is basically for H2. This is the case of H2, two-dimensional, and gamma is finitely generated. And then Okay, long time, nothing, I think. And then Mahan, roughly 10 years ago, using some work of Leininger, Long, and Reed, improved this and got one more dimension. So this means you get SL2C, or if you want to think in terms of hyperbolic space, it's H3. And again, gamma finitely generated. Then Coberda and Mahan. So we keep going, skipping ahead in time, is they prove that yes, if, so now they get any dimension, and gamma should be a regular cover, regular abelian cover of a hyperbolic manifold. Sorry, of an not just hyperbolic, but sorry. Arithmetic. Okay, and I think it's open for all other G. It's open for gamma infinitely generated in these first two results. Yeah. So if you want to restate this in terms of group theory, this just means that gamma is normal in some arithmetic lattice, and the quotient group is abelian. Okay. And any questions so far about the history? Okay, so now I can state the main theorem that I want to tell you about. So this is with David and Mahan this year. And it's that, so it's yes to Shalom's question for, actually we cover many cases of G, but let me just stick to hyperbolic space. Actually, let me just state it like this. Yes, for any normal subgroup of a lattice. Okay, so in other words, so if you compare with this result up here, which I think was the state of the art before this. So here you need you have a normal subgroup, but the quotient needs to be abelian, and the lattice needs to be arithmetic. So we remove these two conditions. If you want, this is for regular covers of finite volume manifolds. Let me take a look at the time. Okay, yeah, so some remarks are in order. So this actually works, this works for any G. We prove this for any G, semi-simple. But the only choices of G for which you actually have normal subgroups with infinite quotients are the rank 1 groups. So for the real Lie groups, that means isometries of hyperbolic space, complex hyperbolic space, quaternionic hyperbolic space, and the Cayley hyperbolic plane. And those are all the rank 1 groups. And then, yeah, so we also cover p-adic groups and positive characteristic groups, and there are some more families, but I'll omit that. Okay, and yeah, maybe that was just the remark that I want to make. So let me tell you something about the proof, I think, if there are no questions.
Sorry, so these subgroups might be infinitely generated, is it? Or?
Yes.
Okay.
In fact, if you have if you have a normal subgroup, it will surely be infinitely generated in this case.
Ah, I see. Okay.
This was even the case for this result up here.
Okay.
The abelian quotients. Yeah, good question. And the reason that I think infinitely generated is particularly important to cover is because if you do this construction for the irreducible in products, which is really where my interest in this problem came from. If you do this construction, then these gamma that you get over here out of this construction are surely infinitely generated. Or at least there is no way to control whether they are finitely generated or not. So if you're interested in this application, you need to be interested in infinitely generated gamma, even if delta is finitely generated. Okay, but yeah, good question.
I had a small question too. So
yes.
in going from the result for PSL to C to these regular abelian covers.
Yes, that is correct.
So basically where we upgraded to the normal subgroup case.
Yes.
So could you comment if there are any ideas in going from this 11 to 19 result that will maybe come up in the general?
So this, I think these two are related in some sense in that they both look at the limit sets of gamma and try to, so because gamma has dense commensurator, it will have full limit sets, and then you look at the structure of groups in either in SL2R or SL2C with full limit set. Now SL2R is smaller, so it's easier there. And here it's really, this paper is really, it uses a lot of hyperbolic 3 manifolds to control that. But this paper is, as far as I understand, completely different. And yeah, it uses more the space of harmonic forms, and then it constructs an action of the commensurator on the space of harmonic forms on Hn mod gamma, basically. And the point is that because this thing is abelian, it essentially corresponds to Hn mod lambda. because this group is abelian, it contributes to the homology of lambda. And so you will see it in the harmonic forms. And then the commensurator acts on that. You somehow use that. So I think it's completely different from this paper. I think, yeah, and so you can see that this proof is kind of limited to this abelian scenario, just because you need things to show up in homology. So this group should be abelian, or at least close to abelian. And so we do something quite different to prove our theorem. There will be no harmonic forms. And yeah.
Okay, thanks a lot.
Mm-hmm. So let me tell you something about the proof. So there, in my view of things, so here is the situation. So we have the following groups. We have gamma sitting inside lambda, sitting inside delta. And what do we know about each of these? About gamma, we just know that it's infinite. About lambda, we know that it's a lattice. And delta, we know, is actually dense. And also, this first inclusion is a normal subgroup. This is what we know. And also, delta commensurates. Sorry, yeah, delta commensurates gamma. Okay, so step one is to show that delta doesn't just commensurate gamma, but also this lambda. Okay, this is not so difficult, but it's very useful. And if you want an exercise, then you can do this. Takes a few lines. So let's just take that for granted at the moment. So now we also know that this is commensurated over here, this inclusion. And that means, by the result that I mentioned before by Margulis about lattices with the dense commensurator. So lambda now has dense commensurator. That lambda is arithmetic. And that means, by a result of your very own, now I'm gonna butcher this name, but Venkataramana, I think. I hope my pronunciation is somewhere close to. Is that lambda? So he proved that if you have a supergroup of a lattice, so something that any subgroup of G which contains an arithmetic lattice with infinite index, then you actually know what delta is. So delta is what is called S arithmetic. That just, what that means is, for example, if lambda is SLN Z, which was our arithmetic lattice, prototype of an arithmetic lattice, then delta is SLN Z adjoint 1 over P. And the only difference with in general is that here I have only inverted 1 prime, and with S arithmetic I am allowed to invert more than 1 prime. So, but he proved that anything containing a lattice, containing an arithmetic lattice, is basically you take that arithmetic lattice and then you invert some primes, which is a really wonderful result, and especially for us, because we now know what delta is. So that's the first step. that we know what delta is. And the second step is that you consider the following situation. So we have delta, and we can quotient by gamma, and we can map this to, we can quotient further by lambda, and then this has a fiber which is lambda mod gamma. This is a kind of fiber bundle, but of discrete of just sets. I don't know, discrete spaces. But what I would like to do is to, I hate discrete spaces, or I mean, if something is just a set, it's not useful. So I would like to, there's a groupification construction that we do. And this is maybe the main technical tool that we use. So what you can always do is, if you have some subgroup, sorry, if you have a group which commensurates some subgroup, you can complete. And this is a construction due to Schlichting. I think it goes back to the 70s or the 60s, or and it's kind of a bizarre construction, but the definition is that the Schlichting completion, which we write like this with the double quotient, is you consider, well, maybe I'll say it in words, it's better, is okay, maybe, sorry, let me first say, you consider the action by translations. So this this tells you that delta is a subgroup of bijections. And this is crazy abstract and seems like completely pointless, but delta is a subgroup of bijections. And you can topologize this group of bijections. And there's obviously there's only one way you can topologize it, which is by pointwise convergence, because you just have a set. So what are you gonna do? But remarkably, this turns out to be useful. You set the completion to be the closure in this group of bijections. Now, surely this is pointless, right? So the first time that I think we realized that this construction might actually be useful for something is that if you take delta to be this Is Arithmetic example and gamma to be the arithmetic one, then this completion actually gives you the p-adic group. Turns out. So at least in this very pretty example, it constructs a very nice group. But now for us, what happens is, so we had this fiber bundle of discrete sets. And now once you groupify, what happens? So everything turns into a group. Lambda commensurates gamma. So I can complete this. And I can, and all of this is a functorial construction. So all the arrows actually, yeah, it all behaves nicely. And so you get delta completed with respect to gamma, and then it goes to delta lambda. And this is some kind of p-adic Lie group. Because of this example, sorry, let me zoom out. Because of this example over here. If gamma is arithmetic, then the completion gives you just a p-adically group. So the same thing happens here. This one we don't know because we don't know gamma. And this one, actually, it turns out that this is just the quotient lambda mod gamma because gamma is already normal in lambda. So this, in other words, this quotient up here was already a group. So when I groupify it, a group stays a group. So this one, nothing happens. And basically the rest of the proof, so this is like page, 2 or 3 of the paper, but the idea is now to show this is this sequence splits. That is to say, and actually this it's not quite what happens, but morally, it's what happens, that this thing in the middle is a product of these two. Okay, it doesn't really matter. And now the punchline is that I can project to the first factor, which is a discrete group. And if you now think of delta inside, so what you built is delta to lambda mod gamma is a quotient of delta. But if you're familiar with S arithmetic groups, then at this point, all the alarm bells go off because this is impossible. So Margulis normal subgroup theorem says that because delta is S arithmetic, any quotient is any infinite, sorry, how to say? Any quotient is okay, maybe I should say it like this. Any normal subgroup is either finite or finite index. There's nothing in between. Okay, so in other words, any quotient is either the kernel of this map is either finite or finite index, but the kernel contains gamma, so it must be infinite. So in the end, since it contains gamma, it's infinite. It must be finite index. And so the upshot in the end is that lambda mod gamma is finite. And therefore gamma is basically the same as this lambda, and lambda was an arithmetic lattice. So gamma is also an arithmetic lattice. I think I have to say that this is the most bizarre way that I've ever proved something is an arithmetic lattice in my life, by realizing this lambda mod gamma as a quotient of an S arithmetic thing. But whatever works, right? So I think I have, do I have 4 more minutes or should I?
Yeah.
So I think this is what I wanted to say about the proof. Of course, I skipped for you the, and if you want, I can say more about this, but why this sequence splits. But I thought instead I would tell you, I feel like I owe you at least some dynamics. And so I wanted to tell you a little bit about what might be next and how this relates to dynamics. So, so in general, suppose that you have, suppose that we're in this setting of this Shalom problem. And delta is dense. Now, what you could try to do, and actually this is the very first thing we did, is to mimic Margulis' proof when gamma is a lattice. And this proof, unfortunately, breaks in two places. And the first is that when you study gamma acting on the boundary of the symmetric space of G, it loses ergodicity. So this is something that Margulis used, which holds if gamma is a lattice. Well, at least we don't know if it's ergodic. And the second is that even if you do that, you only prove that Margulis his argument only shows that gamma is sub-arithmetic. Which means that it's contained in an arithmetic group. And so if gamma is a lattice, if you have one lattice contained in another lattice, then the two have to be the same up to finite index. So Margulis is done at this point. Proving this containment proves essentially equality up to finite index, so it's good. But if you don't know that gamma is a lattice, then, I mean, it's just some subgroup of this group, so it could be anything. We also have a result in this general case, very different from the previous one, but I just wanted to advertise it and maybe ask a question. So assume that we don't have this first problem. We don't know how to deal with this first thing, but we do know how to do the second one. So assume that gamma acting on the boundary of G, and we need more than ergodic, we need doubly ergodic, but okay, same general idea. Then first of all, we get Margulis' argument still works, so gamma is sub-arithmetic. And actually, if G has property T, then gamma is arithmetic. And now, interesting phenomenon is that if G does not have T, then the following happens. Then G mod gamma, then maybe I should say it like this, then Brownian motion on G mod gamma is recurrent. And this also implies that, not trivially, but can make it work, that lambda mod gamma as a graph has an irreducible recurrent random walk. So we would like to show, and I think it's fair to say that we tried quite hard to show that this graph is finite, okay? But somehow we cannot show that it's finite. We can only show that it has this recurrent random walk. So in some sense, it's small, maybe not finite, but at least not too infinite. Anyway, so question for the geometers or for those who think about random walks is, do you know any spaces for which this happens? And of course we have more. Somehow there is this commensurator hiding in the background. Like this is not just any space. It is a space with all these virtual symmetries, but which we seem to not know how to use at the moment. Yeah, I think, sorry, I already went 2 minutes over, so I should stop there. Thanks very much.
Yeah. Thank you very much, Wouter. Thank you very much.